Essere qui. Stasera è la prima volta che parliamo di reinforcement learning in generale, quindi io e Daniele, quindi speriamo di fare una presentazione utile magari per chi vuole avventurarsi in questo mondo. Un attimo che... ok. Allora, volevo fare due parole su chi siamo noi, così molto velocemente. Noi siamo di Orobix, che è una società di Bergamo. Lavoriamo sull'ingegnerizzazione di sistemi basati su AI. Siamo fondati nel 2009, abbiamo fatto un sacco di progetti nel tempo, siamo certificati per medical device. Questi siamo noi, in realtà ce n'è qualcuno in più adesso, stiamo crescendo. Questo sono io, dalle spalle si vede, e questo invece è Daniele, che è là, lo riconoscerete comunque. Siamo un po' di ingegneri, qualche matematico, fisico, qua ci sono anche Giorgia e Roberta, che sono queste, questa è Roberta, e Giorgia è dove sei? Di là, ecco. Quindi se volete dopo magari possiamo fare due chiacchiere rispetto a quello che facciamo. Il nostro lavoro quotidiano è leggere un sacco, capire cosa viene fatto dai big un po' del deep learning e cercare poi di portarlo in problemi che ci vengono posti nel mondo reale, non che loro non risolvano problemi del mondo reale, ma problemi comunque a scala molto più piccola rispetto a quelli che vengono risolti dai grandi gruppi, che possono essere problemi nell'ambito della life science, della salute, o problemi nell'ambito manufatturiero, per esempio, controllo qualità, robotica, eccetera. Quindi facciamo applicazioni medicali. Noi siamo nati nel 2009 come società che faceva analisi di immagini medicali, usando algoritmi non di machine learning, ma non so, i soliti filtri, equazioni di derivati parziali, eccetera, e siamo arrivati al machine learning proprio perché non riuscivamo a risolvere alcuni problemi che ci venivano posti. Quindi questo è un po' il nostro, quello che facciamo tradizionalmente. E poi, essendoci affacciati sul deep learning, abbiamo visto che quello che sapevamo poteva essere anche trasferito a problemi industriali, per esempio di controllo qualità o di ottimizzazione della produzione, ottimizzazione vincolata e robotica. Quindi facciamo una serie di abbiamo una serie di applicazioni tutte verticalizzate però sull'utilizzo di sistemi di deep learning e così via. Chiaramente attorno a questi poi bisogna, una delle sfide è creare, intanto formulare il problema nel modo giusto, perché non è detto che avendo un algoritmo di deep learning i tuoi problemi sono finiti. I tuoi problemi sono altrove, non è il deep learning il punto. Che il deep learning vi dà la possibilità di risolvere problemi in modo abbastanza semplice, se vogliamo, posto che formuliate la domanda giusta di fronte ai dati giusti. Quindi questo è un primo problema. Il secondo problema è come portate poi a terra, cioè fate funzionare in produzione un modello che avete sviluppato. Va bene, quindi qua chiudo un po' quelle che sono le nostre attività. E prima domanda, mi è stato chiesto di parlare in inglese. Cosa faccio? Parlo in inglese, in italiano? Cosa faccio? Qualcuno qui... Oh, inglese. Ok, so I'll get back to the first slide and okay. Let's switch to English now. Okay, so we use reinforcement learning for a few projects, and so we got accustomed to working with these models. Daniele, who's here, who will talk in about half an hour, 40 minutes. Will show you something practical, and he is the one that was more involved in reinforcement learning in our group, but we're planning to use it increasingly in optimization problems. So whenever you have an uncertain situation and some behavior that you can optimize somehow, then we would like to use that over more classical constraint optimization problems that we currently solved using traditional methods. So meetup today will be a presentation on the basics, and here I will not, I'm on the fence with respect to the slides I prepared because they're fairly technical, but I think there's a need, if you want to get into reinforcement learning, there's a few things you have to understand, maybe not every single detail, but there is something to the formalism of reinforcement learning that will make your life easier if you know it when you read a paper. Otherwise, everything will be blurred and not clear. So my goal for tonight is giving you the basic nomenclature that allows you to go into a paper and read it and understand something about that. And I will try to cover two main groups of algorithms. One is Q-learning, and the other one is policy gradients. And then we'll move on to Daniela's presentation. He'll show you a bit about OpenAI Gym, which is a nice set of environments that you can train your algorithm against. And then he will show you a few algorithms implemented in PyTorch and a couple of examples of agents that he trained probably this afternoon of the simple environments that you can find on the internet. The slides I will show you, I didn't prepare them. They're mainly taken from these two sources. One is Fei-Fei Li's course at Stanford, CS231. It's a popular course that you can go up and check. The slides are available. And also the deep reinforcement learning tutorial by David Silver, the AlphaGo guy. If you want the reference on reinforcement learning, you can read, if you have patience, you can read the Sutton's book, which is very comprehensive. It doesn't move fast, but it's really dense, so you have to put some effort in reading it. But when you read it, then it's like you read, the Tolkien book. You've done it, and it's good. Reinforcement learning bumped into popularity when DeepMind wasn't Google DeepMind, but it was DeepMind at the time. Google didn't acquire it yet. Published this paper on Nature, on the front cover of Nature. Nature is this famous journal, and for hardcore, usually you could find geology, biology, medicine covers, and it was the first time in history that they published a computer science cover. And this was because DeepMind had devised this algorithm based on the reinforcement learning, but coupling reinforcement learning with deep learning that could solve and beat human performance on this type of Atari games. I remember them. I'm not sure many of you remember them since you're younger than me. But essentially, it was one algorithm that didn't have any notion of what the actual rules were. That was trained on many games and was capable of being equal or superior to human on any one of this game, each one of this game. And this was important. This was a big deal because it used pixels as an input, and it could control left, right, and shoot, and this kind of controls as an output. And by just using the raw pixels and the score, it could devise strategies. And so I will try to show you. Oops, sorry. Yeah. It's working. Nope. Wait. Sorry about that. Yeah, I have no idea where my mouse button. No.
I will train it later. So I
Hmm?
will show it later on. I trained the thing.
Okay, okay.
So we can see it.
Yeah, that's not important. Anyway, you will see that the at the beginning the paddle catches the ball, and then after a few episodes, the agent learns that it's much better to dig a tunnel in here and let the ball break the wall from behind than constantly trying to catch the ball. And this was a one example of an agent becoming really good at the job without knowing the rules. We are trying to apply this kind of approaches to, for example, robot controls.
Hello world, it's Siraj, and YOLO, you only look once. That is the demo for today's video.
Okay.
We're going to build an object detection algorithm called YOLO, you only look once, for real-time
Yes.
video. So you can feed this thing an AVI, an MOV, any kind of MP4 file, and it's going to be able to,
I don't know.
in real time,
What is
like
it?
this demo that you're seeing behind me that I'm running off of my laptop, in real time,
Is it me?
be able to detect
Yeah. It was okay. So it was the YouTube video I tried to start, and it ended, and it got to the next one automatically. Sorry about that. Okay, so this is an example we always show. It was a robot that, oh sorry, that was trained to attach this piece onto this bar, and the inputs were the force sensor signals coming from here. So whenever the robot touched the ground, for example, with a component, it would sense a force in this direction. And when it was there was a successful hook of the component, then it would sense a force in this direction. So using a very low amount of episodes from here, the robot learned how to make this move autonomously. You can see, sorry, again. Okay, you can see the neural network starting here. And it doesn't go very fast because the controls are only up, down, left, right, and tilt. So it doesn't control the joints individually. But even doing every 250 milliseconds, one command to keep for 250 milliseconds, in just 80 episodes, the system learned how to attach the piece. And we randomized the position where the robot grasped the piece. And also, if you took this away, it was fun because the robot would go down, down, down until it touched with its fingers and then start moving sideways, because he didn't know he didn't have the thing anymore. So he went down, and the strategy was go down until you feel something, and then when you feel something, it means that you touched and you have to go sideways. So if you removed it, it went down until the fingers touched anything. So it was a nice clue. It kind of generalized to this behavior without learning the trajectories, but learning a strategy. So how can you do that? And I can show you the code is really small for this kind of control. So we get into the general idea of what a reinforcement learning algorithm is. Just one question for you: who of you have already studied or are working with reinforcement learning at all? Okay, wow, that's quite a few people. So yeah, so this will be introductory for sure. There let's say, in very general terms, reinforcement learning deals with uncertain environments and agents immersed in these environments, and agents that react to reward signals that can be continuous or even very sparse in time. For example, if I have an agent that has to find a treasure box in a room, the agent will receive a reward only when it finds the treasure box, not before. So there's this problem of reward attribution that is quite that makes reinforcement learning quite difficult. If I'm here and my treasure box is over there, the fact that I'm turning right or left doesn't make a lot of difference right now, but at some point I have to go towards that direction, right? So at some point I will have a few moves that are important to get to the treasure box, but the reward will be a cumulative reward from here to the treasure box. So, and probably at the beginning I'll be randomly moving around the room, and so sometimes I'll get to this and to that and through that, and by repeating episodes, a few of the moves I make will become more important than others. So they will get, I have to figure out a way to get those moves, get the right reward, the most of the reward, because they will have led me to the treasure box more frequently. Of course, it takes a lot of episodes to get to that point. Okay, so and if the episodes were short, like 10 moves, then it would be easy. If the episodes are thousands of steps long, the job is a bit more difficult. Okay, let's introduce the main ingredients of a reinforcement learning problem. I have an environment, which is something that, given a state and an action, will give me a next state and the reward. So the job for the environment is providing a new state and a reward for that step. In this case, the reward is the reward in the step. It's not the cumulative reward, okay? It's just the reward from state ST to state ST plus 1, okay? And it's a number. The agent is the algorithm that, taking a state, will figure out what action to make, and will learn, given a state. Okay, I have ST, the state at the present time. I make an action. Okay. The environment will tell me, this is your next state and this is what you gained in this step. And the job of the agent is to figure out a way so that next time the reward will be as high as possible, essentially. This is the learning part of the agent. But when the agent has learned already, of course, the job of the agent is just to provide the action for given a state. Okay. So let's get a bit more precise definitions of these terms. And this is very important to get if you want to read a reinforcement learning paper. So at each step, at time t, the agent, you remember the arrow going this way in the previous slide, executes the action AT, receives an observation, and receives a scalar reward. Okay, while the environment receives an action, provides an observation, and provides a new scalar reward. So it's quite simple, but it's important. So let's see a few examples. You'll find this one in all possible forms, because this is something that can be trained with a few minutes of training. It's a cart pull problem. Essentially, there's a cart that can go left and right, and your job is to maintain this mass it's an inverted pendulum. It's a classical problem in control theory that you can also solve with reinforcement learning. So what's the objective? Balance the pole. And the episode fails if this angle grows too much, if it's too high in one direction or the other. The state is the angle, the angular speed, the position, and the velocity. One observation would be, can't I just use angle and position and derive the other two from the history? The job of the state is to be a complete description of of whatever I have to know to determine the future. So it's very important that the state contains also any time derivative that you need to determine what the evolution will be, of the evolution of the system will be. Okay, so the state has to be, and we'll see why in a second, will have to be a complete representation of the evolution. Otherwise, the environment will not be able to produce a new state given an action, because it will need all the history to the minus infinity. While if you have a complete state, then it becomes a well-defined operation to know what the next state will be. Okay. The action is the horizontal force applied to the card, and the reward is, well, the reward could be anything, right? Because you could say, okay, I will give you a very negative reward if the angle grows too much. Or I will give you a tiny reward that each time step you make it, you don't fall. Okay. Crafting a good reward is basically 99% of the job of reinforcement learning. Well, I shouldn't say that. It's 20%, and the 80% of the job of a reinforcement learning person is fiddling with parameters with no particular strategy. Right? That's true though. It's really true. So yeah, so you have, as your job is to define the state well, and the state is also what your agent will perceive about the world, right? You could give it the color of the car, it wouldn't be important. If you have a car that runs on a track, you could determine the position of the car on the track in many possible ways, right? If you have a track in 2D, X and Y, you could define the position of the car as X and Y. Or you could define the position of the car in a car-centric way. So how far it is from the border of the track. And this makes a lot of difference. So whatever the agent feels it's really important to define very precisely. And the actions, this is another decision point when you do reinforcement learning, because sometimes your actions are continuous, they're not discrete, but sometimes they are discrete. In the cases where they are discrete, then it's okay. You can say left, right, up, down. It doesn't take much decision. But if you have actions that are from 0 to 1 continuous left and 0 to 1 continuous right, up and down, then all these things can lead to a decision of whether to discretize your actions, to make 3, 5, 7 levels discrete, because there are many more algorithms that work well with discrete actions than continuous actions. Continuous actions is a bit more tricky. So this is another decision. And reward is everything. And you can change reward also depending on what happened. For example, in the robot, I cheated a bit because I said, I give you a reward the first time you feel that you touched the ground, the table. And then I deactivated that reward, because otherwise the agent would continuously touch the ground, and I would say, no, stop it. Yeah, it's like teenagers, right? So you have to be careful giving rewards too easily. Okay, robot locomotion. This is another example. Let's talk about objectives and state actions and rewards. Objectives make the robot move in a certain direction. The state is a bit trickier here because it's the angle and positions of the joints. So we have a continuous state. Problems subdivide into discrete state, discrete actions, or continuous state, discrete actions, or continuous state, continuous actions. In this case, it could well be that we are in a continuous type of problem, because we have a state that describes the angles, and the torques you apply on the joints, like in the robot, are also continuous. And again, here the reward is nothing sophisticated. At each time step that you're upright and going forward, then you get a reward. And if you look at one of these videos, you see things moving really in a weird way, but satisfying the reward. And if you want the agent to move in a way that it's more realistic, then you have to act on the reward. And sometimes it's hard to act on the reward to get to an effect that it's so obvious to you, but you have to make it learn through a reward signal that, at least in this standard reinforcement learning approaches, that's sometimes frustrating, but that's one of the tricky things. Atari games, you'll see a couple later on. Here, the Atari game challenge was complete the game with the highest score, so that we would know the score. The state, it's interesting because it's the raw pixel inputs of the game state. So the actual RGB values of the screen at one particular point in time. In fact, I think they batched 4 successive frames. So you could see this one plus 3 in the past stacked together, and this was this state. The action is just left, right, up, and down. So no continuous. This is discrete by design. And the reward is score increase or decrease at each time step. So just the score here was more logical. And just to close this illustration, game of Go. I think many of you saw the work that DeepMind did with Go. It made a lot of noise because it was good noise because it was a big deal. The objective is win the game, and here you see the attribution problem popping up here. So the game might last a lot of moves, and in something complex as Go, every move has had a chance to influence the fact that you win the game, but it's not obvious which one. So when you reinforce all the moves you made in a game you won, you're also reinforcing moves that you did incorrectly. So the algorithm somehow has to cope with the fact that you will reinforce good moves and bad moves, and you have to hope that the reinforcement of bad moves cancels out when you play a lot of games, so that the reinforcement of good moves kind of pops up. Right? Okay, the state is the position of all pieces, and in fact, we'll see at the end of the presentation, but what they did was treat this as an image and use a convolutional neural network to do a part of the work. So this was the state. The action is where to put the next piece down, and the reward was very simple. So the simpler the reward, I think the better your job was at solving something, but you have to have I think, very good formulation of the problem to be able to shrink your assumptions in the reward. Okay. So, are there any questions here? Okay. Yeah.
I have a little question.
Sure.
In the Go game, you show that you get reward 1 at the end of the game.
Yeah.
Does it mean that you still get 1 reward of 0 for every move you do during the game? Is the reward given at every step of the agent or not?
No.
Okay.
You just get nothing until you eventually win.
Okay, so there is a nil reward, let's say that.
Yeah, yeah, a 0 reward, yeah. Yeah. Okay, so presentation, the fun will come with Daniele, so bear with me for another 20 minutes, and but at least, yeah, as I said at the beginning, I really want to get you through some of the basics, so that even reading an implementation of the algorithm becomes clearer. Otherwise, I think it's a bit obscure. Okay, so what is experience is a sequence of observations, actions, and rewards. Okay, so this constitutes an experience. Well, the state could be a summary of experience. This is a different slide set from the previous one, but you could let's say that a state is produced by a summary of experiences. So, okay, so you got to a certain point with certain rewards, and so at some point your system in the learning process where you get rewards is at some point. So in a fully observed environment, though, you can omit all the dependencies, as we were saying before, and have that the state is just a function of the observation. Maybe I wasn't clear in this passage. If my environment is not fully observed, I have a nasty dependency of my current state from all my history, as we said before. But in a fully observed environment, my description of the observation is sufficient to provide me a complete description of the system that doesn't depend on time. And this is an important point that we'll see in a minute.
I'm sorry.
Yeah.
In the previous example, what is a fully observed environment and what is not?
A fully observed environment is an environment where my description at time t is sufficient to determine my future.
So in the previous example, it's like the game of Go, it's fully observed?
Well, yeah, because if I know the position of all pieces, I can go on. I don't need to know the history. In the card pull example,
It's not fully observed.
if I just have the angle and the position, or the angle of the velocity, this is not enough, because the dynamics of the system will determine with how much strength I have to move this to keep it up, because there's a momentum as well. So I need to know the angular speed of the mass.
So this is not fully observed.
Well, if I include angular speed and horizontal velocity, then it's fully observed.
Okay.
But it's important to do that, because otherwise you have a dependency on time.
Okay.
What's a policy? Policy pops up every time when you read the policy. The policy is your holy grail. When you have the policy, your agent plays with policy, and your target is learning a policy. What's a policy? It's a function that can be either deterministic or stochastic, that maps a state of a fully observed environment into an action. What's an action that derives from the state? And typically, I want the action that maximizes by the sum of the rewards I get until the end of the episodes, okay? Which is called the return. If policy is deterministic, I can say, okay, I have a deterministic function like the logarithm of the state. It doesn't make any sense, but okay, and I get the action. Stochastic means that I have a certain probability distribution of an action that will probably lead me to the maximum, what my best chance, right, to get to the maximum return given the state. And why does it need to be probabilistic, stochastic? Well, because the environment is uncertain, so I don't know what will happen in the future, right? If I have a room and the treasure box always in the same spot, then it's deterministic. There's no problem. It's always there, okay? And my policy will be a table. Depending on where I am now, just go straight or go left and right, and you get there. Stochastic, well, the treasure box is not always in the same spot. So what do? Well, maybe I have a sensor that sees my room, and so if it's not here, I don't see it. Probably it's over there behind the corner. So I have to go there and look there. So these are all things that are probabilistic in nature. There's uncertainty coming. In the carpool, uncertainty is more on the initial conditions, for example. I don't know exactly, but I can basically it's not very uncertain. Maybe uncertainty is the mass. I don't know. Another very important concept is the concept of value function. So we said policy, state, reward, okay, observation, which is kind of almost overlap with state, and agent. Now we have value function, another very important concept. The value function is a prediction of future reward. Future reward means I get the reward at every step, okay? We say here future reward to mean future reward until the end of time, till the end of the episode, okay? How much reward will I get from action A in state S? Okay, when given a state S that describes the environment completely, if I do this move, do I have any idea of how much reward this move will buy me? Okay. The Q value function is called also action state function. Gives you the expected total reward, so the integrated until the end of times, from state S and action A, from a combination of state and action. So given the state, given this action, what will be the total reward at the end of the episode? Of course, this will be inaccurate in a very uncertain environment. It doesn't matter. So this is my best guess. Under policy pi, the policy is whatever function from state to action. So if I change my policy, then of course Q will change because I will behave differently. So my prediction of what will be my reward will be different. And then there's a concept of discount factor. So if I'm here and I move in this room, when I know nothing, things will be a lot more uncertain than when I know a bit more about things. And so the past, okay, the past actions have a tendency to blur in importance with respect to more recent actions. So you discount the reward you got in the past. Okay, so you can forget a little bit of your past when you move on in time. Let's see. Okay, this is a formal. We touched upon this already. When you hear about Markov decision process, essentially it's something we already talked about. It's a formal foundation under reinforcement learning problem. Markov property is current state completely characterizes the state of the world. what we've said a minute ago, completely observable. So Markov property is that if I know the state, I can determine what will happen next, given a few other things. Okay, it's non-dependency on time except what I have in the state. Okay. The state is the set of possible states. Okay, this is the space where Markov decision process lives. It's a set of possible states, set of possible actions, distribution of reward given a state action pair, transition probability, so distribution of state, next state given state and action, which is also probabilistic. Okay, so what will happen next will depend on my previous state and the action I took, bar uncertainty. Okay, anything could happen because the environment is not deterministic, so I can say, okay, it's all well, but let's say this is the uncertain part that the environment provides. This is the mess that environment provides to me, and this is the discount factor. So let's see how a Markov decision process works, and we know almost everything already. At time t0, the environment samples an initial state from that probability we talked about a minute ago, right? So I have an initial state. Then the agent selection action, the environment gives us a reward, which is also actually probabilistic because it depends on what will happen next. The environment samples the next state, the agent receives the reward in the next state, and then this is how a Markov decision process proceeds, which is exactly what we said a minute ago. Okay, what's the objective of all this? Is find a policy. When you see a star here in papers, it means the optimal policy that maximizes the cumulative discounted reward, which is the sum of all the rewards I get in time times the discount factor, which is the thing that lets you forget over time. Okay. This is one of the environments that is simpler and that you can also use to calculate probabilities by hand, let's say. Okay, so the game is you start from a random position, you know what position this is, and you have to get to one of the stars in the minimum amount of moves possible. Okay, so you have 4 actions, okay, and reach one of the terminal states in the least number of actions, and you can actually tabulate what happens. So the policy, random policy will tell you, okay, from this point go randomly left, right, top, bottom, and this is the optimal policy that comes out of that Markov decision process. By sampling the reward you get with the minimal amount of steps, you get here, from here, here, from here. So you could actually calculate, pen and paper, what is the Q value of each one of these action states, okay? So for example, from here, the Q value of going up is that you get to a reward immediately. The Q value of going this way, okay, is, well, it's lower, but it's now 0, of course, because then the episodes could go this way, and you still get to the error, okay? So you see that by transitioning to a neighbor cell, you get to a situation which is like the one you went before. So you want to know what the Q value is for this. So if you knew the Q value for this, then you could also calculate immediately what the Q value for this one is if you move right. Okay. Okay. So this is the Bellman equation essentially, which is well here. Okay. So essentially, the Bellman equation says that the Q do you remember the Q value function is the action state function that tells you if you're in a state, if you make an action, what will be your what's your best estimate for your what the value of the long-term return, okay, of that pair. So how good is that decision? Okay. So in the case of the Bellman equation, is to know the Q value for state S and action A, I have to know the reward of that action and state, the reward I got, plus a discount factor times the Q value of the new action and state that I find myself in. Okay. And if I can compute that, of course I don't know that, so it's a little utility maybe, but in fact it's not, because then if I already computed that, or if I have an estimate of that, then I can complete my calculation and get to a value that is reasonable for Q. Now I want to show you, sorry. Yeah. Sorry. Let's take a step back, and I will get to the Bellman equation in a second. So we said optimal policy wants to maximize the sum of rewards, and how do we handle the randomness? So we have randomness in initial state, we have randomness in how the environment will react to whatever action we make in a certain state. So what we do to handle randomness, we take the average, the expected sum of the rewards. So we sum all the rewards, but we do it if we know the probabilities analytically, we can compute the expected values analytically, but we can also do it many times and average. Okay. In any case, we have to take the expected value of the sum of the returns to the end of time, and try to find the policy that will maximize that expected value. Okay. So we review the definition of value function. So this is Q in terms of expected value of returns, and it means that I have to maximize the expected value of the rewards times the discount factor given an action and a state. And then there is the value function, which is another thing. It's a different thing. It's very related to the first. And it tells me how good is the action, how good is the state I'm in without the action. So for any action I can take, what is the, what's my situation? Like here, the value function will be high because I'm close to this. Okay. Here, my value function will be lower because I'm further away. And since I get a reward if I go there faster, then my value function will be higher here than here, okay? Because here there's a short way to my price. If I'm talking about Q, the Q function will be higher here up, a bit lower here up, and lower here right, okay? Q function always matches the state and the action. We already saw this one, okay, the Bellman equation. Okay, suppose you know Q, how can you find the optimal policy, you know, in case you know Q. So if you know that this up will be very good, the optimal policy will be to look at all the Q values here, okay, and go up, right? Choose the one that has the highest value. So if you have a state, you look at the value of Q for every actions, up, right, left, and down, and then you select the one that is higher. It's kind of trivial. But if you don't have Q, what you can do for simple problems is simply to start from a Q that you make up and select the Q. So initialize the table, build a table of Qs for every state and every action, initialize it randomly, and then start iterating. So, and say, okay, what's my value of Q for a state and action pair? Let's say some number for going out from that cell. Okay, let's look up what the tabulated Q value in my table of made up Qs was, and then add the actual reward and iterate, updating the value of Q. Okay, for example, if I'm here and I go down, okay, and I will have to update my value of Q for this cell down, and here I will find a value of Q that I tabulated previously, and I will just use that, okay? And I'll start iterating, updating the value of Q for each state and action, and I will converge to the optimal Q that solves that problem. And this is the trivial way of solving a reinforcement learning problem that has a small state and a small set of actions. By just iterating the development equation, I can converge to the optimal policy. What's the problem with this is that I have to tabulate, make a table of values of Q for every state and every action. Of course, I can do that from real world, but I cannot do it for continuous problem, for example, or even for chess. It would be too large. It will never converge. What can we do? And finally, we got to neural networks. I can make a neural network learn what Q is given as an A. Okay, so in the end, what the DeepMind guys did in the Atari paper was to find a way to map the state, the pixels, and the actions, left, right, up, down, or shoot, whatever, to a value of Q that was a good estimate of the Q that the game had. So if I had my paddle here, my ball here, and I go left, then the network would output a value of Q, which means what's the estimate of your final return at the end of the game, which is quite something. It's not easy, but by using a convolutional neural network, they could do it. Okay, so this is deep Q learning. Of course, there's many things you can estimate from so this problem is well defined, but it's too complicated. So you have to break it down somehow and use a neural network to estimate something that you cannot possibly compute. One is it's a value based, so estimate the optimal value function using a neural network. Okay. Another that we use all the time is policy based. You search directly for the optimal policy without caring too much about the Q value, or using also the Q value, but let's say, but optimizing the parameters of the policy. So your policy becomes a neural network, essentially, that given a certain state will output what you should do in that case to maximize the future reward. And then the third is model-based reinforcement learning, where you build a model of the environment that you know works in a certain way, and then you can plan using a model. And this is something that, for example, for the game of Go, if you know the rules, you can use that to do a part of the job. So you can explore, go ahead and know what's allowed and not allowed to build a model of your world that conforms to certain rules. For these ones, the rules are inferred from the rewards or the end of the episodes. And here you can have rules that allow you to say, okay, this is impossible in the future. So you can do something like a tree search to search upon possible futures that you know may occur. Okay, so they're 8 o'clock. I think maybe we can switch to the practical stuff. Of course, I had a ton of slides, but I think it's more than enough. Okay, but do you have questions? This is Pietro, my socio at Orobix. Okay, do you have questions about what we just said? Or do you want to see something about deep Q learning or policy gradients, or maybe you can see them in practice? So good? Okay, good.